Welcome back to Honors Calculus. In this video, we will begin our discussion of Lesson 8, Analyzing Graphs, with ideas related to concavity. So let's just jump right in, get my head out of the way. The idea of concavity is talking about how a graph is curved. So we're trying to analyze the difference between a shape that looks like this and a shape that looks kind of like that. We call curves in this first sense concave down. The cute mnemonic device, when we're talking about something being concave, think about there is a cave, and the cave is underneath the curve here. So this is the space where you can be sheltered. It's concave down. The second curve by comparison is concave up because there is space to hide up above where the curve is. In a more formal definition, talking about this idea, the graph y equals f of x is called concave up if and only if f prime is increasing. The graph y equals f of x is concave down if and only if f prime is decreasing. And a point of inflection is a point where the concavity changes. And so if we change f prime from increasing to decreasing or from decreasing to increasing, that is a relative extrema. Right, so my first theorem, kind of the simplest theorem of the lesson, a point of inflection is a relative extremum of the function f prime. Thinking to the application of calculus in kinematics, where Isaac Newton first developed many of these ideas, if we think about the original function as describing the position of an object, then f prime is the rate of change of that position, the velocity of the object. And if we're talking about how f prime is changing in velocity is called acceleration. Acceleration, the second derivative of a function, is what we are really studying here. So, to find and classify the points of inflection in the concavity, we're going to be looking at the derivative and finding extrema on the derivative, which means we'll be analyzing the second derivative. So for example, we might be asked to find the points of inflection of the function f of x equals x to the fourth minus 4x cubed. Points of inflection are extrema of the derivative. So the first thing we need to do is find the derivative. F prime is going to be 4x cubed minus 12x squared. Next, we want to find critical values for f prime. Taking the derivative of f prime gives us f double prime, which is going to be 12x squared minus 24x. And we set that equal to 0. Factor out the common factor of 12x, it leaves behind x minus 2. And we get that there are two critical values for this function, x equals 0 and x equals 2. All right. Now, just like we did with the first derivative, trying to find the extrema of the function, trying to find the extrema of the derivative, we're going to plot out these 2 points. We're going to test stuff between these points. And determine that f double prime at -1 is going to be 12 plus 24, which is 36. But the important thing is that it's bigger than 0. Positive here. If we test +1, f double prime of 1 will be 12 minus 24, which is -12. But again, the important thing is just that that's negative. So we're negative in this range. And then f double prime of 3 is definitely the trickier one. 3 squared is 9. 12 times 9 is 108. 24 times 3 is 72. And 108 minus 72 is 36. But again, the important thing is that that's bigger than 0. So over here, we are positive. And in fact, the function changes from positive to negative at 0. The derivative changes from, the second derivative changes from negative to positive at 2. So 0 and 2 are both points of inflection. This function has 2 points of inflection to work with. Another thing that we can look at here, remember that we said a function is concave up if the derivative is increasing, concave down if the derivative is decreasing. So we can classify that this particular curve is going to be concave upward to the left of 0 and to the right of 2, and concave downward somewhere in the middle. What exactly that looks like, I have no idea. I don't know enough else about the graph, but we'll see something that kind of looks maybe something kind of sort of like that in some way, shape, or form. Right? That takes us to the second derivative test. If the second derivative of f at a critical point C is greater than 0, then C is a relative minimum. And if the second derivative is less than 0, then C is a relative maximum. The idea here is based pretty cleanly around the basic idea that the concavity gives some restrictions to what a curve can look like. If the second derivative is positive, that means that the function is concave upward. And if a function is concave upward, there is no room in that curve to have anything other than a relative minimum. Or the part of this proof, right, a critical value is not a relative maximum, we can see based on just looking at the curve. There is nowhere in a concave upward curve for a relative maximum to occur. The fact that the critical value is the relative minimum and not just an extraneous value is a little bit more challenging and a little bit beyond what I want to talk about right now. But when you have concave upward, you can see that minimum is possible, maximum is not possible. And when you have concave downward, just the opposite, right? There is space here to have a maximum, but there is nowhere you can have a minimum. If the second derivative is equal to 0, the test turns out to be inconclusive. When the second derivative is equal to 0, that gives you a stalling point in the curve, which could be a point of inflection, right? Something like that. Or it could just be a place where the curve really flattens out. In a parabola, you have a very clear minimum, but in a fourth degree polynomial, not only do you have a minimum at 0, but the curve flattens out and you get this stalled out point, which is difficult to analyze. So those sorts of situations lead to an inconclusive result to the second derivative test. So for example, let's go back to the same function that we were just working with. F of x is x to the fourth minus 4x cubed. We know we already established that the derivative here is 4x cubed minus 12x squared, and the second derivative is 12x squared minus 24x. We used the second derivative to identify points of inflection already. We can also use the second derivative as a shortcut method of trying to identify the relative extrema. We still have to identify critical values first. So we'll set f prime of x equal to 0, which means we have 4x cubed minus 12x squared equal to 0, factoring out the common factor of 4x squared. That leaves behind x minus 3. So we get two critical values, x equals 0 and x equals 3. If I evaluate the second derivative at 3, I get 12 times 3 squared minus 24 times 3. 3 squared is 9. 12 times 9 is 108. 24 times 3 is 72, and 108 minus 72 is 36. But the important thing is that that's greater than 0. We're dealing with something that is concave up. And because it's concave up, there is no room for a maximum. It must be a minimum that we have at x equals 3. Compare that to the second derivative at 0. F double prime of 0 is going to be 12 times 0 squared minus 24 times 0, which is 0 minus 0, which is 0. So at x equals 0, the second derivative test is inconclusive. And because the second derivative test is inconclusive, we do have to go back to just setting up and testing in the general vicinity of 0. Test f prime at, say, -1 and at +1. F prime of 1 is 4 times 1 cubed minus 12 times 1 squared, which is 4 minus 12, which is -8. But the important thing is that that's negative. I'm sorry. That was +1 that I just tested. If I test -1, I have 4 times -1 cubed minus 12 times -1 squared, which is -4 minus, well, -1 squared is +1, which doesn't do anything when you multiply. Right, so in this case, we get the point of inflection, which is not on Extrema. And with that, let's turn it to something for you to try. Consider the function g of x is x cubed minus 12x squared plus 35x minus 16. I would like you to analyze this function, try to find any and all extrema, as well as any and all points of inflection. See what you can do with this one and I'll see you in the next video.